IEEE 519 is a standard for IEEE recommended practice for harmonic control in electric power system. Before I go further, let me quickly introduce myself. I'm Sri Chandrasekharan from the IEEE Standards Association. I'm a Senior Director with the IEEE SA, and I'm also the Foundational Technologies Practice Lead, and I manage the standardization activities in the Asia Pacific region. We are very happy to collaborate with the IEEE PES India Chapters Council. We have Dr. Nagaraja with us from the IEEE PES PICC, who are jointly organizing this particular webinar, along with the expert from the IEEE 519 standards community, Dr. Mark Halpin. IEEE 519, this particular version was published in 2014. And I think it has been reasonably well known in India. People have been following IEEE 519, have been getting queries from various sectors, including the railways also. And this looks at the recommended practice and requirements for harmonic control in electric power systems. So the topics today that we will be covering will, as mentioned in the registration site, it talks about the purpose, intention, and rationale for the approaches recommended in the document, and the relevant harmonics limits, and also the voltage and current limits, and how the different limits are managed, and also possible changes in future editions of the document. We are also having this webinar looking into the practical insights, and we have discussion on use cases of IEEE 519. And so this is going to be a very, very interesting conversation, both on what the standard is developing, as well as how it is being applied, how it is being used practically, and discussions around regulations and guidelines as it is applicable in India. So with that, I would like to introduce our speakers. I will give a brief introduction. Their biographies are big, but I want to highlight some key points. First, I would like to introduce Dr. S. Mark Halpin. He has been the driving force in the development of uniform power systems and power quality standards that promote worldwide reliability and safety. He has worked to create international standards that advance the state of art of power systems engineering. His work in both the IEEE Power Engineering and IEEE Industrial Application Society resulted in creating nearly 40 IEEE power standards. Dr. Mark has also been a key contributor and author to the IEEE Color Book series of power standards, and he enhanced it, thus making it more useful for the practicing engineers. He is presently the convener of IEC TC 77 Working Group 2, which is dealing with the voltage fluctuations and flicker, and he is leading the revisions of IEC power quality standards in the 61003-X series. At this point, I would also like to know that there is also a new project, IEEE P519.1 on the harmonics, which is being worked upon as we speak. I will also introduce our next expert speaker, Dr. R. Nagaraja. Dr. R. Nagaraja is the founder and managing director of Power Research and Development Consultants Private Limited, Bangalore, India. He is the architect and chief mentor for the design and development of the MI Power System Analysis software package. Dr. R. Nagaraja is a senior member of the IEEE and currently chapter representative for Power Engineering Society for the Region 10 West chapters. He is also the chair for the IEEE PES India Chapters Council. He was the co-chair for the first edition of the World Utility Summit WS 2016 and chair for the second edition of the WS 2018, which we did collaboratively along with the Indian Electrical and Electronic Manufacturing Association, IEMA. Without much further ado, I would first request Dr. Mark to give his presentation, and over to you, Dr. Mark. So before Dr. Mark starts, I will just quickly run through the agenda so that people are aware of it. So Mark will cover the highlights for about 15 minutes. Then we are going to have a discussion on regulation and guidelines. Then there will be a open Q&A followed by a harmonic case studies, and then again a Q&A session. As people would have noticed, and now we are becoming very familiar with this platform, all the attendees are on mute. However, please do use the chat and the Q&A window. My colleague, Mr. Ravindra Desai, will also curate the questions, and he will be coordinating it with the speakers and the experts to ensure that all the questions are being covered. Sorry about that, Mark, to interrupt you midway, but I will hand it over to you now. Thank you.
All right. I certainly would like to extend my my welcome to everyone, and also my appreciation for you allowing me to be involved with this session today. So I guess you've heard a little bit about my background. I've been involved with IEEE 519 essentially my entire professional career, more than 25 years now, I think. But in any case, a lot has changed in some regards, but at the same time, a lot has not. So what I want to do is I want to take the first and the major part of this presentation and give the highlights of IEEE 519 2014 edition, the edition that is in force today. And then at the end, I want to share with you the areas where we're working now, and kind of summarize some of the things that you're likely to see in the upcoming revision to 519. And right now, we expect that revision to come out sometime in 2021, probably along toward the end of the year. But of course, with the conditions that we all live and work in these days, it's difficult to to make firm time predictions. But roughly, maybe one more year before the next version. So, with that said, well, I probably don't need that particular version of the presentation. Let's see, back up here, stop that, and change over to the full screen view here. Look, where's the full screen? There we go.
Yeah.
There we go. Oh, I thought that was it. Well,
the next to that one.
Mm-hmm.
So just before the zoom.
Oh, just before that one?
Yeah, this one.
But now everybody sees the.
Yeah. They see the next slide. So
yeah.
Okay, probably you can do it in the slide mode.
Yeah.
So just make it easier.
Mm-hmm.
You can close that next slide, I think.
Yeah, I've got it. Oh, let's see. Mm-hmm. I need the there we go. Let's stop that. There, we'll just do it this way.
Exactly. So
okay. So with that, let's kind of give the overview of 519. First of all, it is critically important to recognize that 519 is designed to be applied at the so-called point of common coupling. Now, the point of common coupling is normally taken as the interface point between the customer and the utility. Okay, the exact location of the point of common coupling in a particular situation is not the overly critical point. The critical feature of the concept of the PCC is to make sure you understand that nothing in 519 is intended to be applied inside a facility or to any individual specific piece of equipment. And that's very important to understand. As you probably well know, of course, in 519, we have both harmonic current limits and we have harmonic voltage limits. The harmonic current limits, of course, are for the users, and the harmonic voltage limits are for the supplying utility. The philosophy behind 519 is what we call a shared responsibility philosophy. We try, from the utility perspective, to adhere to the voltage limits as a form of quality control. In effect, from the utility perspective, the product that we supply is a voltage. Of course, we supply energy, but we do it by supplying a voltage. And that voltage needs to have certain quality characteristics. And of course, in the realm of 519, the quality characteristic that we're focusing on is harmonic content in that voltage. So the utility is responsible for let's say, the voltage quality. And there's two aspects to voltage quality. There are two main factors that affect it. Number one is the impedance characteristic of the network. Of course, the impedance characteristic is largely managed by the utility company and largely influenced by the impedances of the T&D system and various pieces of equipment. The second major factor that drives voltage quality, of course, are the harmonic currents that are produced by network users. And of course, it's the interaction between the impedance, which is largely under the control of the utility, and the current, which is largely under the control of the user. It's that combination that we're trying to manage. So the utility is responsible for voltage. The end user is responsible for current, okay? And we tend to assign these limits to end users based on what we call an equitable allocation process. And what that means is we want to try to allow users who are larger to potentially contribute a greater portion of the overall distortion. And the reason being is because larger users tend to pay more money. And of course, the utility supply infrastructure system is paid for by these users. So larger users pay more money for the system. So in effect, you can think that the larger users own a bigger piece of the utility system. So if they own a bigger piece, so to speak, then perhaps they should be allowed to create greater disturbance levels. So that's the economic or equitable allocation philosophy. So 519, it tries to be economic, and it employs a so-called shared responsibility philosophy. The objective in the end is overall management of harmonics in the power system. So exactly what are we trying to limit here? For some reason, oh, there we go. What do we consider to be a harmonic? Now, this might sound like a trivial discussion, but it's not. In the 519-2014 edition, we prescribe the use of instrumentation that is compliant with IEC 61000-4-7 for measuring harmonic content. And in that IEC standard, the Fourier analysis of the waveform is conducted using a 12 cycle, which is about 200 milliseconds of data. Now, what that does is that produces not just harmonic results at the integer harmonic multiples, but it also produces what we call interharmonics. And the interharmonic content is spaced out over what we call 5 hertz bands. Now, a harmonic and everything that's subject to the limits that we're talking about here today, a harmonic is considered to be the RMS value of the integer number and the 5 hertz bends on either side. So there's a little bit of a, you might say, additional content in a harmonic. If we consider, if you can just kind of watch the mouse pointer a little bit, here's the integer number. And of course, here and here are the 5 hertz bends on either side. So what we're going to call in this example, harmonic X, would be the RMS value of all 3 of these terms, not just the one in the middle. And that's important, of course, because especially in the case of actual harmonic distortion, it's not a stationary phenomenon, which means that the digital Fourier analysis will not be perfect. There will always be some content scattered throughout the spectrum. So those plus or minus 5 hertz terms are not necessarily insignificant. So it's important to realize that needs to be taken into account. So that's what a harmonic is. We will talk later at the very end briefly about interharmonics, okay? But we'll come back to that in due time. So that's what a harmonic is. That's what we consider it to be. So if we're going to establish limits, then we have to have indices. All right, we've talked about how we're going to measure the actual harmonic, but how are we going to, let's say, aggregate it, or how are we going to develop an index to give a limit number to? Now, here we borrow again from our colleagues in the IEC, this time from IEC Standard 61000-4-30. And what we recommend in 519 is 2 indices, what we call a very short aggregated value and a short aggregated value. In effect, the very short index that we use for harmonics represents a 3-second average. The so-called short index that we use, in effect, represents a 10-minute average. So at no point do the limits that we're going to talk about apply to an individual 12-cycle sample set. So what you see in this chart, we never apply the limits to this. It's always aggregated, and it's aggregated either over a 3-second interval or a 10-minute interval. Okay, and we do that for both voltage and current. There's no distinction in terms of voltages are measured one way and currents are measured some different way. Now, how do we actually propose limits? Okay, we've talked about the very short and the short indices, the 3-second and the 10-minute values. But do we simply look at one 3-second interval or one 10-minute interval? No. We look at a statistical characterization of the 3-second and the 10-minute numbers over a day and over a week. Now, what that means is, in order to apply the limits that we're going to talk about, a whole day and a whole week of consistent non-gap measurements are required. Okay, so all the limit numbers and all the tables that we'll go through, all of those numbers apply to statistical characterizations determined over one day or 1 week. It's not possible to apply the limit numbers to 1 hour of data or 3 days of data. That's not what's in 519. We need a day and a week. And we typically will use 95th and 99th percentiles. Okay? So we've seen what the basic harmonic quantity is. That's the number that comes out of the 12-cycle window. We're going to take those 12-cycle values, we're going to aggregate them or average them in effect over 3 seconds and over 10 minutes. Then we're going to take those 3-second and 10-minute numbers, and we're going to statistically evaluate them over 24 hours or 1 week. And we're going to look for the 95th and the 99th percentiles over those days and weeks. And it's those percentiles that are compared against the limit numbers given in the various tables. And of course, everything that I'm describing applies to both voltages and currents. Here you can see an example plot. I don't remember. I purposely don't have the y-axis labeled in this. Because it doesn't matter what the quantity is that's being plotted. We all are well aware of the fact that all harmonic values change over time. And so if you think about this type of variation, certainly at some points in the measurement interval, the y-axis numerical value, which is some kind of distortion, the distortion at some periods is well over 15. And that's probably a percentage. So let's call it well over 15%. At other times, the distortion level is down below 1%. So which one of those values would you want to use to compare to a limit? Well, none of them. Okay, we don't use any of those individual values. We take data like this, collected over 1 day and 1 week, and we develop a statistical profile for it. And to do that, we simply make a histogram of all the data, and then we establish the probability function from the histogram. Once we have the probability function, then it's a straightforward process to extract the 95th or the 99th percentile over 1 day or 1 week. And it's the 95th or the 99th percentile over a day or over a week. That is the value that we compare against the recommendations in the table. As far as voltages are concerned, the actual recommended limits are as follows. The very short, the 3-second indices, okay? The 99th percentile of the 3-second or very short indices should be less than 1.5 times the value given in the appropriate table. Okay, evaluated over 1 day. So at the 99th daily percentile of the 3-second values should be less than 1.5 times the number given in the appropriate table. We'll look at the tables in a minute, and I'm sure most people are quite familiar with the tables anyway. Also, for voltage, the weekly 95th percentile 10-minute values should be less than the values given in the appropriate table. Notice the difference here. For the very short harmonic indices for voltage, we focus on the 99th percentile every day. But we allow a slight increase above the values given in the table. Why? The values in the table historically are designed for steady state conditions. A 99th percentile number that evaluated over 1 day, obviously that's not a steady state condition. That's almost an exception. Okay, so we allow a little bit more, you might say, room. When we think about evaluating harmonic content over a week, well, the conditions that are present for a week are sustained conditions, approach more steady state type behavior, and so we don't allow any more margin. There is no multiplier. All right, so that's what we recommend for voltage. That's the responsibility of the supplying utility. What about the responsibility of the end users? Remember, end users are responsible for harmonic currents. And as with the voltage, we use a statistical characterization over both days and also over weeks. Now, in the case, and of course, that we have actually two different weekly indices that we recommend. Okay, notice that the higher percentile numbers, the less likely they are to be more of a steady state concern, the more likely they are to have some kind of multiplier. The daily 99th percentile, which is statistically speaking unlikely, well, that value, because it doesn't occur very often, is allowed to exceed the values given in the limit tables by a multiplier of 2. The unlikely values measured over a week are allowed to exceed the values given in the table by a factor of 1.5. The more likely values over the period of a week are not given a multiplier. So you can think about this in terms of decreasing severity, if you like. So these are the numbers. In terms of the statistics and in terms of the evaluation period. Again, the critical thing here is to recognize that to implement these recommendations, continuous harmonic monitoring is required over a period of 1 day and over a period of 1 week. There's no way to evaluate these percentiles without that continuous and ongoing monitoring activity. Now, it's an interesting question to ask at this point, and that is, what do we do about which day to choose or which week to choose? Obviously, harmonic levels today might be different than the harmonic levels tomorrow or next week or next month. That's an operational decision that each utility company or perhaps each regulator has to consider and has to make. There is no guidance given for that in 519. To quickly take a look at the actual limit numbers, and we're not going to spend any time at all on these tables. Again, I'm sure everybody is quite familiar with them and they're readily available in the document itself.
So Mark, just a quick interrupt, 2-minute warning for you.
Okay, no problem.
Thank you.
These are the voltage numbers, okay, quite standard. We only have one table of voltage harmonic numbers. Of course, you can see that they apply over different voltage classes. There are 3 current limit tables. In general, all of these current limits are given in terms of percentage of maximum demand current. The 3 different tables apply at different interconnection voltages. This is for the lower voltage interconnection. This is, you might say, what we would call the medium level. I don't mean to confuse that with IEC medium voltage, but this is the medium table, kind of the lower end of transmission. And for the upper end of transmission, we have a final current limit table. All right. Let's see. I think we will hop over that. We've touched all of those bases. And as far as interharmonics are concerned, in the present edition of 519, we recommend interharmonic limits based on light flicker. If you're familiar with light flicker, you might recognize this plot as being kind of 2 versions of the traditional flicker curve, the PST1 curve. So I want to skip ahead now to wrap this up and let you know about the potential upcoming changes. One thing that we're going to do is we're going to relax the limits for even order harmonics. We're we're considering changing the definition of THD and TDD in order to include higher frequency disturbances to try to take into account more modern electronic equipment. We're probably going to remove the 50th harmonic as an upper bound. And again, for the same reason, to try to take into account the actual behavior of modern high frequency switching equipment. We're trying to implement a very clear delineation between the different documents that apply for harmonic control that relate to energy consumers versus energy producers. You may be familiar, for example, with IEEE 1547, which is for distributed energy resources. There are harmonic limits given in that document, but that is for energy producers. 519 is for energy consumers, and we're going to try to really make that point clear. And we're also working hard to expand the interharmonic recommended limits beyond considerations that are just limited to light flicker. So that's a very fast, kind of high-level overview of 519, what it is today, and where we think we're going with it tomorrow. So with that said, I think I will stop and return the screen back and control back to the moderator.
Thank you, Dr. Mark. Thank you for the deep dive into 519 in the 25 minutes or so that you did. I know that it's a heavy topic. I think our next agenda item is discussion on the regulation aspects. So I will hand it over to Dr. Nagaraja for taking it over.
Thank you, Sri. Just can you?
If you are presenting, we are not yet seeing it.
Okay.
Okay, now something is coming up. Yep. Perfect.
Okay. Are you able to see the screen?
Perfect.
And the next screen also?
Yes, everything is good.
Fine. Now, I would like, this is for the discussion. Once again, thank Professor Mark for this insight into the IEEE 519. And let me also thank Sri from, and also Ravindra and all the participants for attending this program. I request Mark to comment on this because at present, this is one of the white paper on the power quality regulation in India, Forum of Regulators, which was published in the year 2015. And if you look at the various states and also the limits, and CA regulation is different. And further, in the 2019, which we are going to further discuss, CA has put forth very stringent regulations, and very clearly they are following the IEEE 519-214. Therefore, now I would like actually how the situation in US, because US also being a very vast country and also the North America and other places, I would like Mr. Mark to comment on whether it should be the state specific or the across India we should have the same standard. I would like Mark to comment on that.
I think, as I understood the question, you're asking about having the same requirements across the different states in the United States. Is that correct?
Yes, whether the different regulators are following the same standard, and also in the North America, Canada also, is there any difference in terms of the standard of application? And do you recommend that in India, even though we have got more than about 25 states, should we follow one standard for IEEE, the harmonic power quality standard, rather than each state following its own standard?
Well, okay. First of all, let me answer the first question first, and that is in the United States, of course, IEEE, the 519 is not a legally binding document until it is adopted either by a regulator or or included in a contract between the utility and the user. In general, all of the states in the U.S. That have harmonic policies are consistent with IEEE 519. Nobody has something that's not in line with 519. In the past, in the 1992 version, the various daily and weekly indices and the percentiles and so forth, those things were not well described in the 1992 version. But in the 2014 version, of course, they are. And states and regulators in states do a very good job of simply adopting those recommendations. As far as Canada is concerned, as you may know, Canada is in some ways two countries. There's Western Canada, which historically was under British influence, and there's Eastern Canada, historically under French influence. And so what you find is the Western utilities in Canada tend to follow IEEE recommendations, whereas Eastern utilities in Canada, particularly companies such as Hydro-Quebec, companies in Quebec province tend to follow more of the IEC recommendations. So that's, I guess that's the situation in North America. And certainly with regard to India, I would recommend that that the entire country consider a single uniform standard. And the reason being is because the nature of harmonics, the potential damaging effect of harmonics, and that of course is what drives the need to limit harmonics. The risk due to harmonics is not a function of a geographical location. If my home were at risk for harmonics, the risk to my home would be the same in the north of India, and it would be the same in the south of India. So from that perspective, it is certainly advantageous and probably desirable to have a single national base standard.
Okay, thank you, Mark. Based upon that, if you try to look, the CEA, that is the Central Electricity Authority, in this 6th February 2019, the amendment to the technical standard for connectivity to the grid code, they have talked about the voltage and also the current harmonics, and they have very clearly specified that the voltage and the current harmonics has to be as per the IEEE 519-2014 standard as amended from time to time. This is the gazetted notification. Therefore, I think all the utility regulators, the state regulators should adopt that, so that actually they can, rather than trying to have the different voltage and the current harmonic limits, they try to follow the IEEE 519-2014 standard only, which has been regulated by CEA in their 6th February 2019 amendment. Here, I would like to ask Mark, what is his opinion? The measuring and metering of the harmonics shall be a continuous process with the meters complying with the provision of the IEC 61000-4-30 Class A. Therefore, I would again ask Mr. Mark to comment whether the continuous measurement is required and what is the practice in US and Canada, whether it is required to do the harmonic measurement on a continuous process, means provide the harmonic meters along with the energy meters and then continuously measure it. Is it required?
Well, that's actually a very easy question to answer, because remember that all of the limits now are statistical indices evaluated over a continuous day or a continuous week. So in effect, continuous monitoring is required. In the US, almost all of our significant customers in modern times have power quality instrumentation permanently monitored in effect in parallel with the energy meters. So it's quite normal to have power quality continuous monitoring for significant customers. In effect, any customer where limit compliance might be assessed is going to have continuous monitoring. Of course, 519 is not intended to be applied to my house or to a local shop or market. In cases like that, continuous monitoring is not present. If a harmonic concern were to develop and the indices needed to be determined, then some kind of temporary monitoring installation would be installed, but it would still be used for at least one day and at least 1 week, because we can't capture the statistical indices without at least 1 day and 1 week of continuous monitoring. Thank you.
Thank you. And the next regulation is the bulk consumer shall install the power quality meter and share the recorded data thereof with the distribution licensee with such periodicity as may be specified by the appropriate Electricity Regulatory Commission. Therefore, again, I would like Mark to again comment what is the practice in the North America, whether actually the consumers are going to provide the power quality meters they are supposed to install, or the utilities are installing it.
You see both ways used in the U.S. In general, for larger users where they have let's say the staff expertise to understand harmonics, and they understand that they may create power quality problems. Those types of end users will typically have their own monitoring equipment. But limit compliance is always assessed based on utility-owned and utility-maintained equipment. And maintenance is a big issue. If compliance with a contract becomes a concern, the utility wants to make sure that any recorded data is in compliance with the applicable standards. In this case, the power quality monitor would need to be compliant with IEC 61000-4-30. And the utility wants to ensure that's true. Some customers, some users will readily accept the utility's data based on that 61000-4-30 compliance certificate. Other customers, they may very well install their own power quality instrumentation. And so sometimes you actually have two power quality monitors, one owned by the utility and one owned by the user, monitoring the same thing. Thank you.
Okay. And it also stipulates that in addition to the harmonics, the various other voltage sags, swell, flicker, disruptions will also be done, and it should be measured. Therefore, again, I would like to comment whether it is only the power quality or the harmonics or the various other power qualities are also measured.
Again, if an instrument is installed that is compliant with 61004-30, of course, it will have as measured indices all of the standard power quality parameters, meaning harmonics, sag, swells, flicker, etc., unbalance. All of those indices are available. Some utility companies will have, let's say, contract clauses associated with, for example, flicker or unbalance. If the utility company chooses to enforce those types of power quality limits, then yes, they would certainly monitor that type of phenomenon accordingly. But it's not. It's certainly not a, let's say, a requirement. For example, if an end user is known to not produce voltage fluctuations and flicker, if that's a known thing about that user, then the utility company is not going to, let's say, pay attention to the flicker indices that might come from a power quality monitor. They're there, but that probably won't be included in the contract for service for that user. So there's a little bit of variation in terms of what indices and what limits are given to what customers in terms of the different power quality phenomena. Thank you.
Okay.
Dr. Nagara, I think we can take question answers.
Okay, fine. You can take the question answer then, Ravi.
Yeah.
It's the last slide.
So, Dr. Mark, there is one question. CT and PT is used to connect harmonic measurement instrument in harmonic polluted environment, whereas CT will give distorted measurement. Please throw light on it.
Okay. The issue of CT and PT frequency response, that is a well-known, let's say, problem. There is a general consensus that conventional CTs and PTs, meaning wire wound CTs and PTs, conventional CTs and PTs have a reasonably accurate frequency response below, let's say, 1 or 2 kilohertz. Above, maybe certainly above 2 kilohertz, the frequency response of any kind of PT or CT becomes questionable. The only way to assess that definitively is by measuring the frequency response of the CT or PT. Obviously, that's not easy to do. It's not cheap to do, but that's the only way to definitively answer the question. Now, with regard to measurements in high voltage applications, particularly for CVTs, CVTs are well-known sources of bad measurement data because the frequency response of a CVT is terrible. But everybody knows that, including the manufacturers. And most of the major manufacturers of CVTs will provide a so-called compensation curve that can be used to correct the frequency response errors. So you might say that we as an engineering community, we're aware of these issues of CT and PT frequency response. At lower frequencies, it's not so much of a problem. At higher frequencies or with CVTs, it is a definite problem, but it is a problem that has solutions, and that is to utilize a compensation characteristic for the specific instrument transformer involved. Thank you.
Ravindra Desai, you have any more questions? Ravindra? Hello?
Yeah, I'm reading the second question. Yeah, sorry, I
Oh.
was on mute.
Oh.
Sorry. Yeah, this is the second question. When we do 3-second plus 10-minute interval analysis for 95 percentile and 99 percentile, there are situations when a point of measurement satisfies 10 minutes criteria but fails in 3 seconds, that is 99 percentile, and leads to confusion and dispute. How do you suggest to solve, and do you plan to introduce priorities in future version? Should I repeat once again, Professor Mark?
No, I understood the question.
Yeah, thank you.
In the United States, yes, it is possible to have a particular measurement interval where one index, let's say, meets the limit, but another index does not. The way 519 is written, users have to comply with all of the indices all of the time. So in effect, of course, 1 week is made up of 7 days. So it is possible that a user could comply with a week limit, but that same user could fail a daily limit. That's possible. If that occurred, it's not a conflict. It's just a fact that that user does not comply with 519. There is no partial compliance concept. It's not you comply with one of the limits but not the other. You either comply with all of them or you don't comply. Thank you.
Thank you, Professor Mark. One more question. There are 3 questions I'll read from the same person. Is there any limit on interharmonics? Is there any limit on even harmonic emission? And why there is a relaxation for even harmonics? Should I repeat? Can you hear me?
Oh, sorry, I was muted. Could you read the first question again, please? Yes, I heard all 3 questions, but repeat the first one, please.
Is there any limit on interharmonics?
Yes, there is. In the 2014 edition, the interharmonic limits are based on light flicker. There are no interharmonic current limits given. The effect of interharmonics associated with a light flicker, of course, is a voltage phenomenon. And so the recommendation in 519 is that a user cannot produce currents that interact with the network impedance so that voltage interharmonics exceed levels associated with light flicker. So yes, there are interharmonic limits given, but they're not directly given in the form of current limits. And that is likely to be retained in the next version of 519. No interharmonic current limits, only interharmonic voltage limits, which used in conjunction with the system impedance can provide interharmonic current limits. So that's a good question. What was the second question?
Is there any limit on even harmonic emission?
Yes. In the 2014 edition, the even order harmonics all even order harmonics are limited to 25% of the adjacent odd order harmonic. So if you look at the tables for currents, you will see the odd numbers listed, but there's a note in the text that says even order harmonics are 25% of the adjacent values that are listed for the odd harmonics. And what was the third question?
Third, I'll club with some other questions so that people at large will be benefited. Why even and odd harmonics have different limits, and why relaxation for even harmonics?
The reason that even and odd harmonics have different limits is mostly historical. In the original development of 519 back in the 1980s, at that time, the harmonic producing characteristics of equipment was dominated by odd order harmonics. Properly functioning power electronic equipment, think about, for example, a 6-pulse rectifier. A properly functioning rectifier does not produce even order harmonics. However, if the rectifier becomes, let's say, damaged, or it malfunctions, or something along those lines, it will begin to produce even order harmonics. That is an abnormal situation and an abnormal condition. And so it was believed to be acceptable to limit those even order harmonics more strictly. That's one of the reasons. There are 2 or 3 other reasons, but I think I'll just give that one in the interest of time and move on to the other. What was the next question?
Due to renewable penetration at distribution system, power quality issue is customer centric. If so, current 519 IEEE 519 standard required any further customer side limits?
I hear the question, but I don't know that I understand the question. Perhaps the person asking it can ask it a little bit differently.
Okay, whatever is your understanding, I think you can reply on that.
Read the question one more time, please.
Yeah, okay. Due to renewable penetration at distribution system, power quality issue is customer centric. So current IEEE 519 standard required any further customer side limits?
Okay. I'm going to answer the question as if the question was, in effect, does 519 require anything else for, let's say, for energy producing penetrations? And the answer to that is no, because 519 already addresses in one of the notes energy producing facilities. A facility that is intended to produce energy is limited to the most restrictive row in the appropriate current limit table. If you look at the limit tables for current, there are several rows in each one. And if a facility is an energy producer, for example, like a distributed energy facility, if the facility is a producer, then they are limited to the most restrictive or the top row in the appropriate table. Thank you.
Thank you. So my last question. In a power plant, VFD is at 415 volt, that is LV. Plant has 11 kV substation, bus, and 132 kV GIS. So common point of coupling shall be 11 kV or 132 kV. Which one should be considered?
I think I would, but in order to answer that question, I would need to see probably a single line diagram to make sure I understand where service is provided. In general, the point of common coupling should be taken as the point that is closest to the user premise. But that point should also be available to provide service to a completely different user. So in the case of the example given in the question, if the 11 kV point, if another different user could be served from the 11 kV point, then that point would be considered the PCC. If, however, the what was it, 130, 131?
132.
132. If the 132 kV point, if that were the closest point to the user from which another user could be served, then the 132 kV point would be the PCC. That's how you make that determination. Thank you.
Thank you, Professor Ma. I hand over to Dr. Nagaraja. Over to you, Dr. Nagaraja.
So now Dr. Nagaraja will be talking about the use cases. So over to you, sir.
Okay. Are you able to see my slides?
Yes, sir.
Fine then. Thank you, Professor Mark, for this insight into the practical aspects of the IEEE 519, IEEE recommended practice. Now, in this session, you're able to see the second slide?
Yes, sir.
Okay, fine then. I am going to discuss about the practical case studies, try to understand how the simulation studies can be conducted. One is the measurement, where actually we use the various instrumentations and then try to measure the harmonic for the existing system. But if it is a proposed system, then we also conduct the various simulation studies. Therefore, we'll try to understand what is this harmonic power flow. We will also understand the limits and its interpretation. I will try to explain what some of the interpretation with respect to the IEEE 519 limits, and consumer and also the utility perspectives, and also the illustrative examples. The one thing is harmonic power flow. We need to understand the fundamental component of the current flows from the source to the load. This is what we need to understand. Therefore, if you look into this, the fundamental component, assume that actually there is a 100 MVA 10% impedance, purely reactive load. The source voltage is 1 per unit here. This is the point of common coupling, say, where the consumer is getting connected. This is and the 1 per unit voltage is there. I draw the pure 100% reactive current. The impedance is 10%. Therefore, 100 MVA, 1 per unit loaded. Therefore, 0.1 per unit will be the voltage drop. The voltage will be here 0.9 per unit. Therefore, in case of the power fundamental component, the voltage is maximum at the source and it is minimum at the load point. Harmonic current flows from the load to the source. Assume that actually this is a nonlinear load which is actually injecting a current, fifth harmonic, which is about 10%. that corresponds to 437.39 ampere is the fundamental current. 10% of that is 43.7 ampere. That corresponds to 0.1 per unit. What happens? You have to understand that is a equivalent current source with the source voltage. This is the ideal source, very high fault level. Therefore, this transformer impedance only comes into picture. Therefore, I am injecting a current which is 0.1 per unit, fifth harmonic current, and it is an ideal source. Therefore, there is no fifth harmonic voltage here. Therefore, the impedance, again, if you take the linearity with respect to the fundamental is 0.1 per unit, fifth harmonic is 0.5 per unit. Therefore, the voltage here becomes 0.5 per unit into 0.1 per unit, 0.05. Therefore, VTHD for the fifth harmonic distortion becomes 5%. This is what we need to understand. But the harmonic frequency, voltage is maximum at the load and minimum at the source. Here the voltage is 0 and it is maximum at the load point. This is the fundamental principle we need to understand whenever we try to understand the harmonic, how actually it is going to affect our systems. I am not going to talk about the various limits, but someone was asking actually the even harmonic limits. Yes, it is 25% of the odd harmonic limits. Therefore, it is not a relaxation. In fact, actually, the relaxation is not the proper word. It is actually the more stringent rather than the relaxation. Even harmonics limits are more stringent compared to the odd harmonic limits. And this is the voltage distortion limits. Now, from 69 kV to 161 kV, therefore, if you look at the various current order limits, okay, now let us try to see what it means. One is the ISC by IL, that is the short circuit level at the PCC to the load current. This is what we call it as ISC by IL, where IL corresponds to the maximum load current and the demand current. Here, one thing is very important. When you talk about this load current, the magnitude is also very important. Sometimes, for example, most of the time, my load current is 100 ampere. The harmonic current may be, for example, 2%. But it may so happen that when the load current is very low, it may be just 1 ampere. Harmonic current may be 15% also. Therefore, that is also very important. Therefore, we need to find out the statistical and also the spectrum of that, and then only we will be able to tell whether the harmonic limits are within the limit or not. What happens at the injections as per the IEEE 514 with ISC by I load of 10? This is one small calculation to understand what is the meaning of the harmonic penetration, and if all the harmonic limits are at maximum, what happens? We have considered here the system which corresponds to ISC by IL. It is less than 20. Okay, ISC by IL is less than 20. Therefore, the harmonic limits you can see here. Third harmonic is 2. Fifth is 2. Therefore, you can see here these are the harmonic limits. 5th, 7th, 11th, 13th, 17th, 19th, up to 29th only has been considered in this example. ISC by I load is 10, which implies the fundamental, the source impedance is 0.1 per unit. If at all you need to get the current, okay, ISC by I load of 10, the source impedance corresponding to that 1 per unit current, okay, it corresponds to 0.1, therefore 0.1 per unit. And corresponding to the different harmonic frequency, then assume that the linearity, it becomes 0.5, 0.7 corresponding to that, because we are just trying to multiply this with the harmonic order n into XL. Okay, therefore it is 0.1 per unit, therefore we are trying to multiply that. A harmonic percentage maximum as per the IEEE standard. If you see here, it's a 2, and again, for example, 11th harmonic and the 11th harmonic, 13th harmonic, it is 1. Therefore, you can see 11th and the 13th it is there. Then the percentage voltage distortion, just multiply this current, source impedance current into the voltage, you are going to get what is the distortion. If you do this distortion, total demand distortion, okay, TDD, if you try to look at the current and total demand distortion, it is the square root of the current distortions. Therefore, it comes to 3.38, and THD, harmonic distortion, which actually is the square root of the individual distortions, which comes to 3.36. Now, what is the limit? THD limit percentage as per the IEEE is 2.5. Therefore, what it means is, when all the individual harmonic current injections are at maximum, both voltage and current distortions are violated when it comes to the TDD and THD. Because you can see here, these are all the individual values, and this is the maximum TDD. Therefore, you can check that actually all the values will be maximum. Next thing is what happens with the same with the ISC by I load of 20. What it means is you are getting connected at a place where the source is very strong. ISC by IL 10 is a weak source. Compared to that, ISC by I load of 20 means is a strong source. Same current injections. There is no change in the current injection percentage. There is no change, but the system fault level has increased. It's a very strong source. What it means, you can see here now the TDD. Okay, there is no change in the TDD 3.38, but you see what is the limit available here? It is 4. Okay, it is 4. We are well within the limit. THD, because the source impedance is low, the voltage distortion is also low. Because the source impedance is low, the voltage distortion is also low. Because of that, the total harmonic distortion THD is 1.68, which if you can compare, the allowed THD is 2.5. Therefore, it is within the limit. Therefore, the consumer is only bothering about the current harmonic injection. If the fault level is higher, system is stronger, voltage distortion will be within the limit. Current distortion is consumer perspective. This is very important for us to understand in the harmonic analysis. Consumer can only control the current distortion. Voltage distortion is utility perspective. Therefore, utility has to ensure that the voltage distortion is within the limit while giving the new connection. For example, in the existing system, if the source fault level is very low, means the impedance is high, he should not try to connect many consumers. This is what actually the IEEE 519 talks about. Next thing we need to talk about is background harmonics. Assume that there is a 132 kV source, 100 MVA, impedance is 0.2 per unit, the fundamental frequency impedance is about 0.2 per unit. Fifth harmonic current, if at all you tell that in this grid, there is a background harmonic of 2.5 per unit, already the voltage harmonic distortion of 2.5 is available, 2.5% is available. Voltage harmonic distortion of 2.5% is available. What it means is, there is some current source, fifth harmonic current source, which has got actually the 0.025. That is the 2.5% current you are injecting here, which is going through the source. There is some equivalent current injection, which is going through the source, which the impedance is 0.2 per unit. At fifth harmonic, it becomes 1 per unit. This 2.5% fifth harmonic current flowing through the source is giving a background harmonic of about 2.5%. Now, with this background harmonic current, assume that the consumer is getting connected. Assume that there is a 10 MVA, 10% impedance transformer is getting connected with the fifth harmonic current of about 2.5% on the fundamental 437.4 ampere. What it means is, this is going to increase. This current may be still within the limit, but the voltage distortion is not within the limit. What it means is, if there is a background harmonic in the grid, consumer cannot be responsible. Consumer cannot be responsible. Consumer cannot be responsible. But even though his current distortion is within the limit, current harmonic are within the limit, the voltage harmonic limit here may not be acceptable. Utility, while giving the new connection, he has to check what to do. That is what is very important. Utility perspective is the voltage harmonic distortion. The consumer perspective is current order distortion. With this, we'll try to do a very typical case study where we have got two consumers at the PCC, point of common coupling. From the harmonic perspective, consumer one is dirty. Maybe he's generating the harmonic current. Consumer two is very clean, no harmonic current. Illustrations is done only with the fifth harmonic current. Source fault level, both strong and weak sources are considered. What are the various steps for the harmonic power flow? And series resonance, mitigation methods we'll try to discuss. Therefore, this is what we are trying to talk about. This is the system, 66 kV grid, fault level is 3-phase and single line to ground fault level is 1000 MVA, X by R ratio is 20. Therefore, this is how the grid is modeled. And then, this is the consumer one. Therefore, what is the point of common coupling? This is the PCC because this is the consumer one and this is the consumer two. Two consumers are getting connected at the utility bus here. Therefore, 66 kV bus here is point of common coupling. Assume there were to be some other consumer getting connected here, then actually this becomes the point of common coupling. But here, this is the consumer transformer. He has got a 66 per 11 kV transformer, 10 MVA, 8% impedance. And there is a load here, which is 5 megawatt, 0.9 power factor. In the harmonic simulation study, what we do is, we do the power flow analysis at fundamental frequency to find out what is the maximum load current, and assume that actually the maximum load current is 300 ampere at 11 kV. Reflected current at the PCC here becomes 50 ampere. Therefore, I load here corresponds to 50 ampere. Assume that actually this is the maximum load current, then actually the I load becomes 50 ampere here. This is what we are going to consider in the calculation of ISC by IL. 50 ampere is being considered here. Now, this is the consumer who has got actually the 10 MVA 8% impedance, and this load power factor is very poor, 8 megawatt, 0.8 power factor. Therefore, in order to mitigate the load power factor, in order to see that actually he's going to maintain a very good power factor, he's going to have 5 MVA capacitor bank here. Now let us see what are the various cases, what will happen if he has got mere 5 MVA capacitor bank without the current limiting reactor here, what happens, that also we'll try to understand. Next, we do the short circuit analysis. Fault calculation is going to tell you what is the fault current. Therefore, ISC corresponds to here. You create a 3-phase fault here. The grid source fault level is 1000 MVA, 66 kV. Therefore, it is going to give about 8700 ampere. Therefore, ISC is 8700 ampere. ISC by I load, 8700 divided by 50, that corresponds to 174. With respect to this now, ISC by IL, we need to check in the corresponding table. What is the table? You have to check corresponding table, which also looks for the voltage here. Up to 69 kV, there is a table. And above 69 kV, there is one more current distortion table. Therefore, what we need to do is 66 kV is below 69 kV. Therefore, we need to refer that table. And also corresponding to the current ISC by IL, I load 8700 divided by 50, 174. Therefore, if you look at the table now, acceptable fifth harmonic current distortion is 12% and acceptable fifth harmonic voltage distortion is 3%. Therefore, 12% and 3% is what actually is acceptable. Therefore, short circuit study is going to tell you what is the maximum fault current, and also you can do it for the minimum fault current, and then try to find out what is the ISC by I load. Then comes the frequency scan. At the fifth harmonic, the transformer is modeled, transmission line is modeled, source is modeled. You try to find out the driving point impedance at fifth harmonic. There is a separate illustration for how to model the transformer, how to model the load, at what frequency. I am not going to discuss that. But based upon those stipulations and the standards, each and every equipment is modeled. Then you try to find out what is the driving point impedance, Thevenin equivalent impedance at the driving point impedance here. It is what you are going to see here. At the fifth harmonic, you can see here, one is actually the grid impedance. The fifth harmonic, you can see that fundamental this impedance is increasing. At fifth harmonic, there is a dip in the impedance. Subsequently, okay, it again started increasing. You look at the consumer premises, 2. This is the consumer premises 2, bus number 5. The impedance started increasing. At fifth harmonic, it is falling. Then again it started increasing. Now the thing is, it is maximum here. At the consumer impedance, it is maximum here. At the PCC, it is minimum. Now the question is, why this type of behavior? Let us understand here, what will happen corresponding to fifth harmonic here. This is very important for us to understand that there may be series resonance in the system, thinking that actually he is the culprit, he is injecting the harmonic current here, but entire harmonic current, rather than going to the source, it is coming to the consumer too. Why it will happen? Transformer is 10 MVA, 0.08 per unit. Fifth harmonic transformer impedance becomes 0.4 per unit. Capacitor is a 5 MVAR, 1 per unit. BC is 1 per unit at that voltage. Therefore, the per unit value is very important. 5 MVAR BC value. Therefore, capacitor is 10 MVA, 2 per unit. 5 MVAR 1 per unit, 10 MVA 2 per unit. Fifth harmonic XC becomes minus 0.4 per unit. What will happen? This transformer with the capacitor, this resonates. It's a series resonance. Therefore, whatever the harmonic current is being injected by consumer 1, 5 ampere, because 30 ampere is what actually we have considered, because the fundamental current is 300 ampere. Fifth harmonic current, 10% of that is the 30 ampere is what is being injected. Reflected current here is 5 ampere, 66/11 kV. Therefore, the reflected is 5 ampere here. Therefore, the current is 5 ampere. Now it has got two parts. One is to go to the source. Other is actually, it sees that actually this is a resonating. Therefore, this becomes a low impedance path. Therefore, out of this 5 ampere, rather than going to the source, it is coming here. The second consumer is getting affected. No fault of his. He is getting affected. This is what is very important for us to understand. There is no fault of him, but this person is injecting the current, he is absorbing. This may happen even in our utilities also. Assume that actually this is a 66 kV substation where actually there is a industrial system getting connected, and the utility system has got a 66/11 kV transformer. That is their substation, 66/11 kV substation. And then in order to improve the power factor, he'll get a capacitor. When this consumer is injecting the current here, that capacitor along with the inductor It may so happen that actually it may resonate corresponding to the fifth harmonic, entire harmonic current is getting absorbed here. What is the effect? There can be overheating in that capacitor because of the current, and also the deterioration of the insulation level because of the voltages. That is what actually we need to check here. Therefore, the harmonic frequency scan is very, very important. Frequency scan is going to tell you, is there any resonance point? Is there any resonance point? Is there any frequency where actually there can be a resonance in the system? Now you may ask the question. Yes, I don't know what will happen. Today I have already designed my system. But tomorrow it may so happen that some consumer will come, how to safeguard my system. We'll try to look into that later. Therefore, when you do the harmonic power flow, you'll be able to find out what is the current, what is the magnitude of the current, and how the current is getting distributed. In the harmonic power flow, you'll be able to get on the single line diagram, the complete power flow you'll be able to get. Also on the same single line diagram, you will be able to find out what is the distortion, voltage distortion. For example, the TDD 5 within the limit, acceptable limit is 12%. You can see here it is 10% is the current you are injecting. Why? Fundamental current is 300 ampere. Fifth harmonic we have injected 10%. It is still within the acceptable limit. Voltage harmonic distortion, it is 0.1, but acceptable limit is 3%. Okay, this is 3%, therefore still it is acceptable, 0.1%. All values are in percentage, therefore this is still acceptable. Also, you'll be able to find out on the bar graph corresponding to the various buses. Once you do the harmonic simulation studies, you'll be able to find out what is the harmonic distortion also corresponding to the various buses. What you are going to see here is at the 11 kV bus, consumer bus number 3, that is at the harmonic voltage harmonic distortion is maximum because he is injecting. As I told you, from the source, when you move towards the load where you are injecting the harmonic current, voltage distortion is maximum. But you see this poor customer, he's a very clean customer, but he's within his plant at 11 kV, voltage distortion is more. No fault of his voltage distortion is more. Rather than having a simple capacitor without a current limiting reactor, assume that actually we design the capacitor bank with a 6% current limiting reactor. What is the advantage of having a current limiting reactor? When you energize the capacitor bank, there is an inrush current. That inrush current gets minimized. If you have to energize two parallel capacitor banks also, that time also that problem will not be there because the inrush current gets minimized. And also the voltage surge also will come down. Therefore, these are the advantages in having a current limiting reactor. Why 6%? Now let us see what will happen if we have a 6% current limiting reactor. XC is 1 per unit. XL is 6% of XC, that is 0.06 per unit. But resonance frequency NXL is equal to XC by N. Therefore, N square corresponds to 16.67. That is for N corresponds to approximately 4. Therefore, this resonates at fourth harmonic. If you have a capacitor with 6% current limiting reactor, it resonates at the fourth harmonic. And what we just concluded, even order harmonics are very minimum. And if it is a perfect power electronic equipment where the first half cycle and the second half cycle in the sinusoidal waveform, it is symmetric. There is no, you can do the Fourier analysis. If it is a symmetric waveform, there is no even order harmonics. Therefore, on the sine wave, you can try to do the Fourier analysis, and you can always conclude that if it is a symmetrical, there is no even order harmonics. Therefore, if you tune at 6% current limiting reactor, it gets tuned to the fourth harmonic. Therefore, what will happen corresponding to the fifth harmonic? Now you see the frequencies plot with the current limiting reactor. At the grid, impedance is increasing. At fourth harmonic, it is minimum. But we are not injecting the fourth harmonic current. Yes, it is minimum at the fourth harmonic, but actually we are not injecting the fourth harmonic current. When it comes to the fifth harmonic, the XL and XC both are in series. Because both XL and XC are series, when you try to inject the fifth harmonic, it becomes inductive in nature. It is no more a capacitor because the fundamental frequency is capacitive. At fourth harmonic, it is resonating. XL is equal to XC. Above fourth harmonic, that current limiting reactor along with the capacitor, it becomes inductive circuit. Therefore, you can see here impedance starts increasing. With that, what will happen? The entire harmonic current is flowing back to the grid. Fifth harmonic voltage will increase now. Why? Because the harmonic current is flowing through the source impedance here. Equivalent source impedance, this harmonic current is flowing. Because of that, fifth harmonic voltage is going to increase. Now, if you see, the current drawn by the consumer 2 from the PCC, the fifth harmonic current is very minimum. Fifth harmonic current is very minimum. Fifth harmonic TDD and also TST, therefore, fifth harmonic voltage here from 0.1, it has become 0.26. Current distortion still remains same, but the current distortion here has come down. Current distortion here has come down. Therefore, what we need to do? Consumer 2 has no control on the grid changes. For example, this consumer has first put up his plant. Then this consumer has come. He is injecting the harmonic current. That current will come here to the consumer 2. But he doesn't know what are the changes that will occur at the grid. Therefore, consumer 2 has no control on the grid changes. Better to design a system carefully such that it is not affected with the changes in the grid. This is very important. Therefore, if we have selected the system rather than the pure capacitor bank with a 5 mA 11 kV 6% current limiting series reactor, whatever happens in the grid, this circuit is not going to resonate. Therefore, this is very important. No fault of a particular consumer, because if there are any other harmonic current being injected, if there is a resonance in the system, it may so happen that actually we may try to start absorbing various currents. Again, you can see here the total harmonic distortion here. Yes, but the consumer who is producing the fifth harmonic current, it is high, but you see here now, it has very well within the limit, very well within the limit. What happens if it is a weak grid? What do you mean by the weak grid? Here the fault level is just 200 MVA. Assume that there is a long 66 kV line. Normally the 66 kV, if it is a dark conductor, can take about 27 MVA. Therefore, still you will be able to load. But assume that it is a long 66 kV line. The fault level here may be just 200 MVA. Now, if you look at actually the various currents, the current direction is very important. Most of the time, if you see at the various instruments, okay, the current direction is also equally important. Normally, we don't look into those directions. The direction is with respect to the fifth harmonic voltage here. This is the fifth harmonic voltage. The voltage angle is available here. This is the fifth harmonic current, and the angle is available here. Immediately, you'll be able to know this is the current here, which implies actually this is the injection. This is the trial. Because with respect to the voltage, with respect to the fifth harmonic voltage here, current is trial here. Most of the time, what we have seen is we don't look into the angle of the current and also the angle of the voltage corresponding to the harmonic voltage and the current. We only look at the magnitude. Magnitude is not going to tell you Magnitude is not going to tell you what is the direction, who is the culprit, who is getting penalized. You will not be able to know. Therefore, in many measurements, we ignore this. But what I suggest is always try to have a look at the voltage magnitude and also the angle, current magnitude and the angle. That is going to tell you with respect to the corresponding voltage, corresponding harmonic voltage, what is the direction of the current. This is very important. Same thing in the weak read now. Fifth harmonic PDD and also the THD, weak read, fault level 3-phase, SLG is 200 MVA. Therefore, now you can see here, this is 10.06. What is acceptable now? Current distortion not acceptable limit now, because ISC by IL now is different. Corresponding to that, acceptable limit is 7% only now. Earlier it was ISC by IL was 157, but now the ISC by IL is less. Corresponding to that, the current distortion is not acceptable. Voltage distortion is still acceptable, 1.01%, but the acceptable voltage limit is 3%, therefore is still acceptable. Now what will happen? This current distortion is not acceptable. This is 7%. Therefore, what this consumer has to do now? This consumer has to design a filter. Otherwise, he is not going to comply to IEEE 519. He is not going to comply to IEEE 519 because acceptable distortion is 7%, but what the distortion is going to get is 10%. Therefore, now let us see how to design the filter. Now, because his load power factor is corresponding to 5 megawatt, 0.9 power factor, that is about 2.5 MVAR. When we try to design the filter at fundamental frequency, it can give some harmonic current, the capacitive current also. That is, it can inject the reactive power to the grid here. But the advantage, you'll be able to maintain the better power factor also here. Therefore, fifth harmonic filter, we need to design a fifth harmonic filter here, which is going to act at the 2.5 MVAR at fundamental frequency, and at fifth harmonic it is going to resonate, so that you are going to have a unity power factor, so that you are also going to maintain the very good power factor here. Once you provide a filter, therefore what I will do is I will just try to get into the software tool, and then therefore what is it we are going to do here? We need to design a filter here. Therefore, you can go for a user-defined filter. Is a fifth harmonic, voltage at 11 kV. It is a 5 MVAR, 2.5 MVAR filter. 2.5 MVAR means at fundamental frequency, it is going to give 2.5 MVAR. Q factor, normally based upon the X by R ratio, this Q factor is defined. Therefore, you can take about 20 to 50. That's how actually based upon the X by R ratio, the Q factor is defined. Therefore, we can take it around. Now you can see here, with that 2.5 MVAR, what is the inductor and also the capacitive value will be available. With this inductor and the capacitive, you'll be able to find out how the system is going to behave.
The screen is blank.
You're not able to see the screen?
Yes, sir.
Okay, 1 second.
Blank or black? Yeah, now we can see. Thank you.
Okay, let me just close this. I think 1 second. You're not able to see now?
No, we cannot see now. There's a grid now. Now we can see.
Okay, I think I need to share. Stop. Now you are able to see?
Yes, now we can see.
Okay,
Thank you, sir.
fine. Therefore, what we have done is basically we are trying to design the filter. The filter
Sorry to interrupt. Again, grid is seen. We cannot see your screen.
Okay, then.
Now we can see. Yes.
Okay, fine. Then. Therefore,
Now
what
it is
we try to
visible.
do is we design the filter here, and then based upon that, we'll be able to do the analysis. Once you do that, you're able to see now.
So again, it's a grid.
Okay, okay.
Now we can see.
Fine. Therefore, once this you try to do, the current distortion will be within the limit and also the acceptable limit. That's how actually the filter is designed. And with the filter, you'll be able to ensure that actually even with a weak grid, 6% current emitting reactor with a 2.5 mA fifth harmonic filter, the entire values are within the acceptable limits. Therefore, what is very important to understand here is when you do the harmonic measurement, that can be done for the existing system, but the simulation studies are very important whenever you want to do the harmonic analysis for a proposed system where the injected values of the harmonic currents are available from the manufacturer equipment data sheet. Then you can always do the harmonic power flow studies, harmonic simulation studies to find out how the various distortions are going to look, and then you'll be able to take proper mitigative measures. Normally, these type of studies are done whenever you want to plan the SVC or the STATCOM in the system, or whenever actually you want to design the capacitor bank in the system. You would like to see that the system, there is no resonance point where the entire harmonic current in the grid is being absorbed by the capacitor bank. Therefore, these are the various studies using the simulation studies we will be able to conduct and then try to see how the system is going to be performed. All the studies, whatever we have done simulated here, we have done using the MyPower, but we will be able to use any other software tools to ensure that actually proper simulation can be done, and based upon that, you will be able to analyze the given system. Thank you very much.
Thank you, sir. We can take question answers now again.
Definitely.
Yeah. So first question, it is to you. In many states, the power supply is extended to railway traction in 132 kV or 220 kV in phase-to-phase mode. Does this system pollute the EHV system through harmonics? Though there will be voltage difference, but does this system give rise to third and triple neutral harmonic current, as there are zero sequence current and there is no neutral for zero sequence harmonic current to go to the source, when the other odd harmonics, positive sequence and negative sequence, cancel each other?
Okay.
The question?
Fine. Question is clear. Basically, in case of a traction substation, what happens? Will there be any triplet harmonic? Now let us try to understand what is the meaning of a triplet harmonic. There are two things in the triplet harmonic we need to understand. One is a balanced triplet harmonic. Other one is a triplet harmonic itself can be unbalanced. What I mean here is the magnitude may be different. Now let us see the balanced triplet harmonic. When there is a balanced triplet harmonic, basically I sin omega t, I sin omega 3 omega t minus 120, therefore that becomes 360, therefore it is again I sin omega t for this y phase. Then you have got I sin omega t plus 120, 3 into omega t plus 120, again it becomes sin omega t. Therefore, if the triplet harmonic is balanced, Okay, balanced means 3 into omega t plus 3 into omega t minus 120 plus 3 into omega t plus 120 is a completely balanced system. Then it is equivalent to a zero sequence current. Therefore, we always tell that actually that is why when we have a delta star ground transformer, and on the star side, if there is a triplet harmonic current, a balanced triplet harmonic current, it circulates in the delta winding of the HV winding. Delta star ground transformer, there is a triplet harmonic, it is equivalent to a zero sequence current. It circulates in the delta winding on the system side, IA plus IB plus IC 0, which implies there is no triplet harmonic current going out. Now coming to this very specific question in the traction system. Traction system, we normally take RY phase or YB phase or BR phase, RY or YB or BR phase. Maybe it can be 220 kV or 132 kV. In Madhya Pradesh, we had a lot of 132 kV traction systems earlier, but now most of the time we are trying to connect it to the 220 kV. Therefore, we are taking a two-phase supply RY. Then there is a single-phase transformer, normally 25 MVA, 220 bar 25 kV. It's a single-phase transformer. Now, if there is a third harmonic current, what happens? Third harmonic current, okay, yes, it is a single phase now. Therefore, there is a third harmonic current, it is flowing in that winding. Because there is a path for the third harmonic current there, because transformer is grounded there. It is a single phase transformer, single phase supply, transformer is grounded, and then you are taking only the single phase supply. Therefore, the third harmonic current can still flow there. What will happen to the HT side, 220 kV side? 220 kV side, there is a reflected current, but only two-phase currents are going. Therefore, there is no zero sequence current, there is no zero sequence path there. Therefore, it will see it as actually the negative sequence current and only the positive sequence current corresponding to this third harmonic, negative and positive sequence. Third harmonic current will flow there. Definitely it will flow, but it will be reflected as actually only the negative and positive. Okay, it will still flow. It gets reflected. It will flow, but it will be only the third harmonic reflected current will flow there. It will be definitely flowing. But if you try to look at the three-phase system, and then try to resolve zero sequence current, there will not be any zero sequence current. I think Murthy, I have explained you. Is it fine? Okay, Ravindra Desai, you can move on to the next. It will flow. Definitely, it will flow. Ravindra Desai? Hello?
Sorry, sir. I was on mute. Yeah. Sorry. I heard you. Yeah. Thank you, sir. Yeah, for answering that question. This is to you, Dr. Nagaraja. Where in India is the frequency response of CTs and VTs be checked?
Where in India?
The frequency response of CTs and VTs can be checked.
I think you can see at CPRA. I am not really aware. Maybe CPRA may be having that frequency scan where actually you will be able to inject the current, because I remember they must be having some harmonic current source injection. But at that voltage, it is very difficult. CT you may be able to, but I really doubt whether at that voltage, whether you will be able to find out the characteristic at that voltage, injecting that harmonic, and then try to find out. I really doubt. I am not able to answer. Okay.
Yeah. Even they can check at IREDA. IREDA has facility, but to what extent they can check, I'm not sure. So they can either go to CPRI or they can check with IREDA. Next question, sir. Thank you, sir. What is the appropriate location of fixing harmonic measurement instrument? Is it in the substation or at load point?
Both. If you are interested in actually the consumer, basically the consumer, then it has to be at the consumer where actually from the PCC, point of common coupling, where the consumer is getting connected, that is the place where you need to measure the current distortion. Therefore, normally the harmonic meters have got both the current and also the voltage measurements, both are possible. Therefore, if you connect it to the bus and then measure actually the bus voltage, it is going to give the voltage distortion and the current distortion, both you are going to get at the PCC. Therefore, at the point of common coupling, where the consumer feeder is going, you need to measure that.
Okay. Thank you, sir.
For example, I tell you, within the plant, assume that there is a hot strip mill. Assume that there is a steel plant where you have got a hot strip mill, or there is an arc furnace. You want to measure those currents, then you have to connect there. Therefore, the measurement location depends upon what is your objective. At the PCC, you want to ensure whether the harmonic currents are within the limit, or you would like to find out the equipment characteristic when it is running, what happens in case of an electric arc furnace, or a hot strip mill, or a cold rolling mill, what happens. Then you can measure at those points also. Then you are going to get what is the harmonic spectrum that is going to give. The spectrum, you can use it in your simulation model to find out what will happen.
Oh, thank you, sir. Next question. In DSO, to measure TSD, should 12 cycle be considered on the screen?
Again, come back.
I'll repeat, sir. In DSO, to measure TSD, should 12 cycles be considered on the screen? Because TSD is changing with the number of cycles.
Mark, can you just answer that?
Yeah, sure. Yes, everybody is aware that that harmonics are not stationary, to use the signal processing term, but indeed the 12 cycle window has been deemed to be reasonably acceptable in terms of compromise. It's not too short of a window, but at the same time, it's not too long. And remember also that events that occur in a time frame of less than 200 milliseconds, those events are not really going to be steady state anyway. And so even thinking about harmonics at faster time intervals than a couple of hundred milliseconds, that's a stretch, and it's probably more like a transient than a harmonic. It's probably not going to be around long. So the 200 milliseconds is considered to be an acceptable compromise. Thank you.
Thank you, Mark. Because we had 2 or 3 questions only on measurement, 12 cycles measurement. Thank you. So next question, can you throw more light on short time flickers limit?
Is that question for me?
Either you or Dr. Nagaraja.
I think Mark is the best person to answer.
Okay, repeat that question, please.
Can you throw more light on short time flickers limits?
Flicker?
Yeah, flicker limits.
Yes, I certainly can. I'm not sure. There's a tremendous amount of additional information. I think we need a little bit more specific question. I mean, flicker and harmonics are very different. So I'm not sure. I'm not sure even where to start. With
okay, we'll move to the next question. Equipment. I'm going to the next question. Equipment vendors provide only magnitude of the harmonics, not the angle. Does the angle of the harmonic have any impact on the harmonic current TDD calculations and harmonic resonance?
They basically, if they give the magnitude that is sufficient, when they tell that actually the fifth harmonic is there, you assume that it is a balanced fifth harmonic. Therefore, if you when the simulation model, if you are doing a 3-phase model, fifth harmonic, for example, is a 5 ampere. They would have given, for example, 3% would have given on 100 ampere. Fifth harmonic, it becomes 3 ampere. Angle is not required because you are assuming that fifth harmonic frequency, it is actually sin omega t. Therefore, 3 sin omega t, 3 sin 5 into omega t minus 120. Therefore, it becomes finally 3 sine omega t plus 120. Actually it has got a reverse phase sequence. Then the other phase RYB, it becomes 3 sine 5 times omega t plus 120. Therefore, it becomes 3 sine omega t minus 120. That is the value you can give, because you are making an assumption that it is a balance. Therefore, you use those currents. They only give the magnitude, but when you do the simulation, you can take that actually it's a balance in all the three phases.
Thank you, sir. So next question, can we discuss importance of TDD with respect to THD, total demand distortion with respect to THD?
Okay. Demand distortion is with respect to the consumer. Okay. THD, when we talk about, that is with respect to the voltage. Demand distortion is with respect to the consumer perspective, and the voltage distortion is with respect to the utility perspective. Consumer is only responsible for the TDD, is not responsible for THD. Utility has to ensure with many consumers are getting connected with the different TDD values, whether his bus voltage harmonic distortion is within the limit or not. Therefore, the TDD is with respect to the consumer perspective. THD, voltage distortion, is with respect to the utility perspective. Mark, if you want to add something more, you can add.
Yeah, that's a good question. I guess I would offer up maybe two other points in addition to what's already been provided. Number one, the use of TDD effectively captures let's say, the economic or equitable allocation of responsibility, because with TDD, you're using in the denominator the maximum demand current. And so because the denominator is largest, then the percentage will be smallest. So it drives the number down. And what that means is larger users with a larger demand current that pay more for the power system, their actual current in terms of TDD, that percentage is smaller. And so it's easier for them to comply. And that seems fair because they're larger customers and they pay more. So it should be easier for them to comply. And by using TDD, that's one way to do that. The other point is that if you use THD for current, for example, you can have some very high THD values if the fundamental frequency current, which is in the denominator, if the fundamental frequency current value is small, then that inflates the THD. Even though the individual harmonics, they could also be small. If the fundamental is small, you got a little number in the denominator, and that artificially makes the end result THD percentage, it makes it unrealistically high. So for that reason, especially for currents, we try to avoid using THD. Thank you.
Thank you, Mark. This is for you. Supraharmonics and interharmonics going to dominate in near future? If so, can you suggest the root cause analysis? I will repeat. Should I repeat?
No, I heard the question. I'm not sure what's meant by root cause analysis, though, so I'm not sure what to say in response.
Root cause analysis of supraharmonics and interharmonics.
Yes, I heard that, but I don't know what is meant by root cause analysis. I don't know what the person is asking.
Is it why the interharmonics will come? Is it whether the why the interharmonic current will come and why the superharmonic current may come in the system. Maybe that may be the case.
Yes. As I understand, how these are generated, supraharmonics and interharmonics, how these are generated.
Okay. Thank you. Interharmonics are certainly generated by any kind of nonlinear load that is not synchronized with the power frequency. And an easy example of that is an arcing load, because arcing obviously is nonlinear, but it's not in any way synchronized to the power supply frequency. And so it produces distortion over a broad frequency range, not limited only to integer harmonics. Another way that interharmonics are produced is with switching converters, where the switching frequency is not a fixed multiple of the power supply frequency. So basically the switching converter is switching at whatever frequency the manufacturer sets. If that frequency is not a multiple of the power supply frequency, then interharmonics will be produced instead of integer harmonics. Those are two very common sources of interharmonics. And you have the traditional things like cycloconverters, and any kind of AC to AC direct frequency converter produces interharmonics. As far as higher order harmonics are concerned, any kind of modern power electronic converter is switching well into the kilohertz range. And as a result, it's producing harmonics at multiples and divisions of that switching frequency. So, for example, if you have a switching converter in a power supply for an LED light, those kinds of light drivers tend to switch in the tens of kilohertz, and so they produce harmonic distortion in the tens of kilohertz. Thank you.
Thank you very much, Professor Mark. With that, we come to the end of the session. Very impressive and enlightening. So, I sincerely thank Professor Mark Harpin for accepting our invitation to deliver talk on practical insight into IEEE 519 standards on harmonic. Thank you for joining early in the morning from the US, and thanks for your enlightening talk, giving us insight into 519 and harmonics control. My heartfelt thank goes to most welcome. My heartful thank goes to Dr. R. Nagaraja, Chair, PISSC, PIC, PES India Chapters Council, for practical, meticulous explaining of IEEE 519 with the case studies, and for his cooperation support in organizing today's webinar. My thanks goes to all the participants who participate in large number, and success of this is evident from the number of questions we received. Unfortunately, we could not take each and every question, but at least we received tens of questions. I didn't count, but all the questions have noted. Must be more than 50. Based on the questions, we may try to have one more, because your response was very good and we are happy with that. Thank you. This was for you only. IEEE's endeavor is to connect the technical communities and provide a platform or opportunity to contribute. Last but not the least, let me thank Sri Chandra, Senior Director, Standards and Technology, for his support. Thank you.
Thank you, Ravindra. This recording will also be available, right, to the attendees?
Yes, and even presentation will be also shared with all the attendees. Thank you for reminding me that. All the participants will get a presentation of both the speakers, and a recording will put on the web, and then I'll share the link.
Sounds good.
Thank you. Thank you very much.
Thank you all.
Yeah. Stay safe. Good night. Bye.
Bye.
So thank you. Thank you, Professor Mark. Thank you so much. Thank you, Sri.
Thank you all. It was a great event. I appreciate it.
Thank you. Bye-bye.
Bye-bye.
Bye. Thank you once again, Mark and Dr. Nagaraja. Thank you.